Hello and welcome to Mr. Jackson's physics class. Today we're going to talk about complex circuits. Complex circuits are circuits that contain both series and parallel inside. So I'm going to do about two examples, but you can apply it on up. So I'm going to do an example where it's got both series and parallel, but I'm going to treat it like a parallel. And then I'm going to do another one that's got series and parallel, but treat it like a series. So let's do this. Let's say we have a circuit that's got a battery and it's got three parallel paths, which means it got options for the circuit to work. Okay, and so remember, we're going to be using our equations here. We have our equations for series and parallels, and so we have let's give this a 200-volt battery, and let's give this one resistor, and let's say this one resistor is 40 ohms. Let's give this one a series of resistors. So we got two resistors in here. One is going to be 20 and the other is going to be 20. Okay? And then this last one has a 10 ohm resistor. Okay? So how would we solve this one? I got a series in the middle of a parallel. Well, I'm going to treat it like a parallel. I'm going to add these together because I know that series adds together. So we're going to just add these together, and I'm going to put a 40 here in the middle because 20 and 20 is 40. I'm going to put a bracket around here, and that means these are acting like a 40 in the center. So I'm going to treat it as if they're one. Okay? So now what I've done is I've got now a parallel, and so the first thing they pretty much always want you to solve for in any kind of series or parallels, as you see them at the top, is always find the resistance, and either it's going to be called R total or RQ if it's parallel. And that just means equivalent because they don't add up to a total. They act as an equivalent as a team is one. And usually it's smaller than all the rest. So there probably will be a number smaller than 10. Okay? So let's do it. 1 over REQ equals 1 over R40 plus 1 over R40 because they're acting together as a team plus 1 over 10. So the common denominator, I know they all can go into 40. So 40 goes into 40 one time, plus 40 goes into one time, and 10 goes into 40 4 times. And then you want to take your number and flip it over so this RQ gets on the top. And so then you get 40 divided by 6. And so here we go, Claire. 40 divided by 6 is 6.6667. Ooh, that's a weird number, but we're going to cut it off here. And we'll call it 6.67 ohms. Okay? So that's the total resistance in that circuit. Okay? That's good to know. Now, the next thing they almost always ask you is what is the current total through the whole circuit? Now, we know that in a parallel, the current here and here is the whole circuit. Okay? But the current inside of a branch is different. And so we have branch currents and we have total currents. So let's find the total current. And in a parallel, it's battery divided by the REQ. So it's battery, which is 200, divided by the 6.67 ohms. And so clear 200 divided by 6.67 equals 29.98. Get rid of the 8 at 29 and make sure it rounds to 30. So that's good enough, 30 amps, okay? And so that is the current through the entire loop, okay? But since there are branches, in case they ever ask this question, what is the current in the branches? So we would have to use this equation. So we have 3 branches. We have a 40 branch. We have another 40 that act together, and then we have a 10. So let's do that. It says right here in my equations, you just take the battery and divide it by the individuals in the branch. We're going to treat this as an individual. So we get our battery, 200 volts, divided by the individual of 40 ohms. And 200 divided by 40 equals 5 amps. So this one's 5 amps. And again, this one would be equal to 5 amps because it would be 40 together. Remember, I'm treating it as a single, so I've turned it into a parallel. Okay, and then this one would be 200 divided by 10, which would be then 20 amps. And remember, these should always add up the branches to the total. So 5 and 5 is 10 plus 20 is 30. and that is what it is right here as a total current. Okay, that's a true statement. So that's how I would solve for those. But what happens if I ask you, well, hey, if we put a voltmeter in here, what would be the V drop? Well, remember, we taught you one thing. The V drop for every parallel is equal to the battery. So it would just basically be 200 if there's only one resistor. Watch. Voltage drop, okay, and we put it for the 40, the 40. And so we're going to go, voltage drop is the I in the branch, and we found it in the branch to be 5 amps, times it by 40 volts. That's 200 volts. So it feels the whole battery. So this one's going to feel 200. So if I do the voltage drop for the 10, it's going to be 20. Because remember, it's the branch current. So it's 20 times by 10 ohms. That was in ohms, I'm sorry there. And that gives me 200 volts. But now the voltage drop here would be different because they're in series. So in branch 2, we would have 2 drops. It would use up the 200. But if you started here, you would have 200 volts pushing in, and you would have 0 volts pushing out. So each one would use up some of, in fact, half. So it should be 100 and 100 because they're 20 and 20. But let's prove it. So let's do a voltage drop. But as I go through here, I'm actually going through a series. So we're going to do the voltage drop of a series here. So you see how we're mixing them together? So voltage drop of the 20 in the series is going to be current, I current, okay, which starting here, it's pushing here at 30. Okay, so 30. Well, we're going through a branch. Forgive me, we're going through a branch, so I got to use the branch current because that's being pushed through here. It's different through here. Okay, so I'm going to be using 5 amps, 5.0 amps. And then I use the 20 ohms. That gives me 100 volts. And then the other one, of course, it's got 5 amps. So I apologize. I got to use the branch current, okay, because I'm mixing them together, times by the 20 ohms would be 100 volts. So that's how you would solve it. You have to start treating it, putting them together, treating it like a parallel, but then when I go through here, I got to treat it as a series. So that's when you got to know how to jump back and forth between the two. So that would be an example of one where I treat it as a parallel. Let's do one more and treat it as a series, okay? So that means I'm probably going to do, let me do this one I have. So let's do another complex one, okay? So if you want to take a picture of that, you can, a snap picture of that one so you can see that. Okay, hopefully I did it all on the screen. Trying to make sure I keep myself in the screen here, and I also have my equations. So let's say that we have this circuit. We got a battery, and we got a couple parallels that have some single resistors in them. But we added one over here. Okay, and this one's 8 ohms. This one's going to be 12 ohms, and let's make this one 6 ohms, and let's give it a 36 volt battery. Okay, so how would we solve this one? This is up here. It's hard to really call it, it's not a separate path because it becomes a series with this one and it becomes a series with this one. So if I was going to envision this one, I want to turn this into all a series one, and here's how I would do that. I would think of it this way. I would think of it as my battery, and this battery has a 8 ohm right here, and then it goes into this parallel section, which then goes back to the battery. So here I have my 8 ohms. Here I have, I'll put my 6 ohms up there, and here I got my 12 ohms. So what I did is I'm treating it like a series. Does that make sense? So I'm going to treat this one like a series where I took the other one and I treated it like a parallel by putting this one together. Now I'm going to put these together and treat them as if they're going through a series. So we got to get rid of this one first. So my goal is to find the total in the series, but I can't find the total till I figure out what these two act like. So we're going to go over here to the side. We're going to go 1/6 plus 1/12, because remember that's the equivalent, our equivalent, okay, over 1. So 12 is my denominator. 6 goes into 12 2 times. 12 goes into 1. 12 goes into 12 1 time. Remember, I rotate the numbers upside down, flip them over. I get 12 divided by 3. And so that means that this is 4 ohms. So this feels like 4 ohms, but it's in series. So how do we find a series total? So our total for this picture and diagram, it would be 8 plus 4, because that's what they're acting like. So 8 plus 4, 12 ohms would be my total resistance in the circuit. So I have taken my complex and have come down to my total. The next thing, of course, we always want to find the current through the whole thing. And so we want to find, remember, like an A can be here, it can be here, it can be over here. It's going to be the same everywhere, but it won't be the same through here because in the branches it changes, but it is everywhere else in the circuit. So let's find what it could be all the way around the series. And in a series, it's battery divided by total. So 36 volts, okay, divided by the total, which is, we found out to be 12 ohms. 36 divided by 12 is 3 amps. If you're not sure, turn it on here. 36 divided by 12 is 3. Okay? So that gives me the current. But let's say now I go, well, gee, what is the drop as we go around these? Or let's find that we can find the I in the branches. Let's go find the I in the branches, because now we're back to parallel. So let's treat it like a parallel for a second. Just looking at this part. What is the current through here? Here it's 3, but what is it through these things? So we go here, and we have a problem though. If it goes through this resistor, it's going to use up some of this 36 volt battery. So I actually don't know the battery, because so the battery voltage 36 volts here, but once you get to here, it will be less than 36, and if you go through here, it'll go down to 0. Because remember, every time you pass through a series circuit, the voltage keeps dropping. So we actually need to find the V drop through the 8 ohms. V drop through the 8 ohms. And how do we do that? V drop is the total times the R individual. So the total, which is the current total, 3 amps, times the total, which is 12 volts, which is then 36 volts. Okay, so we have the drop is the current total, 3 amps times that, it's going to use up all 36. Oops, I made a little mistake here, guys. I want to apologize. I'm talking about going across the 8 ohm resistor and I put 12 in here. So that was my mistake. This is supposed to be an ohm resistor, and so I made that mistake. I'm going to have to apologize, draw that information back. So it's right here. I needed to do this equation. Voltage drop, I said it's going to be a series. So it's going to be the first drop right here. To make my mistake, clear my mistake up, voltage drop is going to be the current, which is 3, times the resistor I'm going through, 8 ohms. 3 times 8 is 24 volts. So of the 36, 24 are going to disappear. What is 36 minus 24? That is 12 volts. So right here at this spot, 12 volts will be left to push through here. Okay? So I got 12 volts left to push through. So now if I want to find I in the branch, that is 6 ohms, and I in the branch in this parallel section, that is the 12, because I got to do the branches. I need to know the battery power, but I just said the battery power was reduced because it's in series. So you see how complicated it can get? So I got to use 12 here because I've gone through a resistor that's in series with other ones. And so here we go. We've got to use the battery, but the battery would be 12 here. So 12 volts, 12 volts. And this resistor right here is 6 ohms. So it'll go through this branch at 2 amps. And this one's 12, so it'll go through at 1 amps, which they should add up to. Remember, all the branches will add up to the total. So 2 and 1 is 3, so it does add up to the 3 amps. Okay? And now we can get complicated again. And let's say if I put a voltage drop around here, V drop, what will it be? Well, that's going to be simple. We said the V drop is equal to whatever is left from the battery. So the answer for V drop through here, because the 12 volt can push through this side or the 12 volt through that side. So the V drop for either the 6 or the 12 will basically be 12 volts. But let's prove it. V drop is whatever the branch current is. This branch's current right here is 2 amps. You see that? So V drop for the 6 is 2 amps, because I'm using this equation right here under parallel, times that individual resistor, 6 ohms, 12 volts. So I get it back because that's what's true about parallel. So what I'm doing is I'm using series and then sometimes parallel. I just have to be careful when to use each one and understand there's a voltage drop for each one. Okay? So that is how you solve complex problems if they ask you for different things like voltage drops inside of the parallel. It's acting like a series. And so there's an example of where I've turned a parallel into a series and solved it with series and parallels. And then here's one where I had a parallel with a series and I added the series and treated it as a parallel. And so it comes down to practice. They're not all easy to do. You got to take your time and visualize them different. It's going to take time. We'll start off slow and then we'll start giving you some more and more complex problems and have you guys figure some things out. So this right here is key. You need these set of equations, and you need to be able to jump between the two and understand when am I dealing with a series, when can I add them together and treat them as one, when can I add them together and treat them as one. So here's what I've done to keep it as a series. So that's what you got to get used to doing, and we're going to work on that as a team, okay? So thank you very much for joining me. I appreciate it. You have a great day, and we're going to have fun with these, and you have a great day.